Hi, this is Dane Quinn, and today we'll do a lecture on friction for engineering mechanics and dynamics. So, friction is essentially a force that models the interaction between objects in contact. So, anytime two objects are in contact, there are contact forces between those two objects, and one component of the forces resists interpenetration, but the other component of that force opposes the relative motion between objects. And it's this component that we refer to as friction. So our models of friction rely on experimental observations that date back a number of years and include such individuals as Leonardo da Vinci, Amantens, and Coulomb, who lived from 1736 to 1806, who is widely regarded as the individual. No. Our models of friction arise from experimental observations, and there's a long history that's involved in these sorts of things, dating back to such people as Leonardo da Vinci, Amantens, and Coulomb. And in particular, Coulomb, who lived from 1736 to 1806, is associated with the model of friction that we currently use for most sort of beginning engineering dynamics investigations. And now this experimental model, or this model that arises from experimental observations, has a number of different features, right? And one of those is that we assume that the model is independent of the contact area. So the amount of surface area that is in contact between the two objects does not affect the friction force. And that's one experimental observation that has been observed. The second two observations that we try to incorporate involve relative motion. So in particular, sliding between the two objects. And the first of these is that the force is independent of the sliding velocity, which implies that as the velocity changes, then the magnitude of the force doesn't vary, right? It remains constant. And then the second of these observations is that the force is proportional to the magnitude of the normal force. So that component of force that sort of resists interpenetration. Right, so here I've drawn two blocks, right, that are in contact and have the ability to slide relative to one another. So we'll start off and we will identify some directions. Right? In particular, we'll identify ET as the direction that is tangent to the contact plane, and that's the plane defined by the contact between the two objects. And EN is then normal to that contact plane. So given that, we will identify the slip velocity as follows. So let's say that we have this upper block will be referred to as block A. The lower block will be block B. Then we'll let the velocity of A be defined as VA, and the velocity of block B will of course be VB. Then the slip velocity is the relative velocity between these two, and it's defined as VA minus VB in vector form. Right, or writing the scalar magnitude, we assume V slip, so this is a scalar and this is the vector in the ET direction. So again, this is known as the slip velocity. Then, sort of turning to free body diagrams for these blocks, we can identify a couple of forces. So the normal force is the component of the contact force that resists penetration. So this will be N in the normal direction. And then this, of course, is minus N in the normal direction. Followed by the friction force, which represents the tangential component of that force. And this we'll write as Fr in the ET direction, and then on the other block minus Fr in the ET direction. So N is the normal force, and Fr, which again is in the tangent direction, is the friction force. So this is our setup for looking at friction between objects. So again, the model that we most commonly use for friction is known as Coulomb friction. Right? So in order to define Coulomb friction, we need a couple of different things. So in particular, let's look at this block, and this was sort of in the previous picture, block A. This would be the upper block. So now the slip velocity is the slip in the tangent direction, and of course rewriting the normal and friction forces like so. This is the normal force, and then this was the friction force. So in order to properly define friction, we need to identify the force that would be required to maintain stick between the objects. And so that we actually define as the sticking force. So again, we'll say this is F stick in the ET direction. And so if the blocks were sticking, so there was no relative motion between block A and block B, then this would be the force between the two. And we'll use this to help us define the actual value of friction. Right, so basically it looks like this. Right, so this value of friction, Fr, so this is the scalar magnitude here, is equal to the following. It's equal to F stick if there's no relative motion. So again, if these two blocks stick together, then the force of friction is exactly the force that is necessary to maintain stick. Right? So whatever that force is, and that is problem specific, it would come from looking at, say, a free body diagram and equations of motion, and you would determine what that force needed to be in the problem that you were interested in. And then you would say, okay, the friction force is that because the blocks stick. So if the blocks stick, then we know the slip velocity. The slip is equal to 0 because that's kind of how we defined the sticking force. Now, there is a restriction on this. The magnitude of this sticking force has to be less than or equal to mu s times n, where mu s is defined as the static coefficient of friction. And this is a material property. Actually, it's a property that can be experimentally measured that depends on the surfaces that are in contact, right? So this would be something that would have to be given to us, right? So we would identify the static coefficient of friction, and then we would say as long as the sticking force is less than mu times n, mu s times n, and the blocks are stuck together, then they essentially remain stuck together. So now let's look at that piece down here on these two graphs. So basically, the friction force can be anything, and it can be whatever it needs to be to maintain stick, provided it's less than these values. So here, looking at this graph, let's assume that the sticking force or the slip velocity is 0. Right? So what's the friction force? Well, again, it's the sticking force, but it's got to be less than mu s times n. Right? So let's put those values here and here. Right over here, we'll have minus mu s times n. Right? Because after all, this is absolute value. So as long as the sticking force is between these two values, then the friction force is equal to that value. Right? So I can essentially draw that, and then this is the plot of the friction force. Now, what happens if it exceeds these values? Well, we'll talk about that in the next line. But so now let's go over here and look and just draw the corresponding picture, which is the slip velocity versus the friction force. Remember, here we're actually just focusing on the case where the slip velocity is equal to 0, right? So we'd see that the projection of this onto this graph is simply a line, right, that covers this part of the vertical axis from mu s n down to minus mu s n. So now, what happens when there is relative motion? Well, in that case, the friction force is actually known. Again, when there's slip or when there's no slip, again, when there's no slip, then we know exactly the relative velocity. It's 0. But we don't know the force. If there is slip, we don't know the velocity, but we do know the force now. And it's going to be minus mu k times n times really the magnitude, or sorry, the sine of the slip force. And this piece represents the slip direction. Notice that if v slip is positive, then v slip divided by the absolute value is just 1, while if v slip is negative, then v slip divided by the absolute value is minus 1. Right? So this piece represents the slip direction, and with this minus sign in this definition, we see that the friction force always opposes the velocity. So again, here, the slip is non-zero. So now looking at these plots, we see that if v slip is non-zero, but v slip is positive, then the friction force is minus mu n times k. Right? So that'll be a line that looks like this, minus mu k times n. And if v slip is negative, we get plus mu k. This value of mu k is known as the dynamic or kinetic coefficient of friction. And again, it's something that is experimentally measured. So what happens? Well, if the sticking force is outside of mu s plus or minus mu s times n, then essentially the friction force just takes on this value of the kinetic coefficient of friction. So we end up with something that looks like this. So again, if the sticking force is too large, the friction force is no longer able to match the sort of required value to maintain stick, and it changes to mu k times n. And of course on the other side it changes to minus mu k times n. So there's this little jump, as you transition from stick to slip. That is almost always a decrease in the value of the coefficient of friction. Oftentimes in problems, we'll actually take mu s equal to mu k to simplify some of the algebra. But this is basically our description of Coulomb friction. So in cases where the blocks are stuck together, then we know the kinematics. Again, we know the motion, or we know the relative motion, but we don't know the force, and that's something that has to be solved for in terms of the equations of motion. However, if the blocks are slipping, there's relative motion, then we know the force, but we do not know the slip velocity. That would be the thing that we would solve for from the equations of motion. So a lot of the difficulty in friction problems actually comes from these transitions, right? So looking at when do we transition from slip to the left, no slip, slip to the right. So down here I've kind of redrawn these pictures of the kinematics, namely the velocities and the velocities of the two objects in contact, and the forces, friction force and normal force, just for reference. And I'd like to know, when do I go from no slip to slip, or slip to no slip? Well, let's look at the transitions between slipping to no slip first. And those are actually pretty easy. So if I'm slipping to the right, if this upper block is slipping to the right relative to the lower block, so that V slip is positive, well, when do we stop slipping? Well, we stop slipping exactly when that relative velocity decreases to 0. So I can draw a little arrow from here to here. And I can say this transition occurs when V slip equals 0. So now, looking at the transition from V slip negative, which would imply that the upper block is moving to the left relative to the lower block, this transition is going to occur when V slip is equal to 0. All right, so V slip is negative, it's negative, and then suddenly we find that V slip is instantaneously 0, and we transition back to this condition. Okay, so what about transitions between V slip equals 0 and possibly slipping to the left or slipping to the right? Well, what we find is that this occurs dependent on the value of the sticking force. So if the sticking force is greater than minus mu s times n, but less than plus mu s times n, then the block just remains in this state. There's no relative motion, and the two objects stick together. So we'll kind of represent this by an arrow back onto this block. However, what if it's outside this interval? Well, we begin to slip to the right whenever the sticking force is greater than mu s times n. All right, so again, if the sticking force is too large, that's the force that would be required to maintain stick. Then this friction force can't quite meet that, and as a result, it's not large enough, and the block begins to slide to the right. So V slip would be positive. Likewise, if the sticking force is less than minus mu s times n, then the block would begin to slide to the left. So these transitions out of a state of stick depend on the value of the friction force, of the sticking force, relative to this mu s times n. Right, so again, if it's within this range, it just stays where it is and the blocks stick. If it's greater, if it's too large, then friction's not able to match that, and the block slips to the right. If it's too large in the negative ET direction, again, it can't match that, and so the block begins to slip to the left. So this is how these transitions between states of slip and stick work. So that's a pretty good description of friction in general, looking at slip velocities and coefficients of friction and normal loads. And of course this is more complicated because you have these transitions in the problems. And we'll cover some of that in future examples. So thank you very much, and I will see you next time.